that the forcing from the non-carbon dioxide gases is smaller, but it's still significant. It cannot be left out of the accounting. The average surface air temperature of the Earth, annually averaged and averaged over the surface of the globe, has responded, as expected, to those increases in heat-trapping gases. You can see here that the 5 hottest years in the period of good thermometer measurements of global average surface temperature have been the last 5 years. The Earth has been warming more or less steadily for the last 100 years or so, as the increasing forcing from human-caused greenhouse gas buildup came to dominate the natural variability in the climate. Excuse me. We know without question that it's humans that have caused this warming, not just the correlation of the increase in atmospheric concentrations of these heat-trapping gases, but we also have isotope studies and other evidence that prove that the increases in atmospheric greenhouse gases resulted not from natural influences, but from human activities. And in fact, when the effects of the human-caused buildup of atmospheric particles are accounted for, the human-caused increases in carbon dioxide and methane and nitrous oxide and industrial fluorocarbons explain essentially all of the recently observed increase in the global average temperature. There's no scientific doubt about this any longer. In addition, the spatial patterns of the warming match the results that basic physics and climate models predict would result from the observed buildups of heat-trapping gases, of greenhouse gases. And finally, under the much more slowly operating natural influences on Earth's climate, Earth had been slowly cooling for about 7,000 years up to 1750, up to the start of the Industrial Revolution. And it would have continued to cool under those natural influences. We would have been heading for another ice age, perhaps 10,000 years down the road. We solved that problem with heat-trapping gases, but we overcompensated. And here's the picture of the last, basically, almost 13,000 years of global average surface temperature. And you see the nearly 7,000 years of natural cooling, and then this very sharp increase associated with the onset and progression of the Industrial Revolution. But global warming, the term global warming, is a bit of a misnomer. It seems to imply something that's uniform across the planet, global, mainly about temperature, warming, gradual, warming, not heating, and quite possibly even benign. What can be wrong with being able to swim a little later in the fall, to be able to plant a little earlier in the spring? Doesn't sound like it's all bad. That term global warming seems to have confused people, because what's actually happening is highly non-uniform across the surface of the Earth. It's not just about temperature, as we will see. It's rapid compared to the capacity of ecosystems and human societies to adjust, and it's harmful for most places and most times. What that means is that there will be some benefits from the changes in climate that are ongoing in some places for some period of time, but the longer it goes on, the more uniformly negative it becomes. A more descriptive term, rather than global warming, would be global climate disruption. I've tried without success to get that term lodged in the vernacular, and it failed dismally. It has sunk without a ripple, but it is a better term. So let me show you some of these distinctions between what is really happening and global warming. This shows the non-uniformity in the temperature change. This is the annual average temperature in the warmest year on record, 2016. Over that period, the average warming was just about 1 degree Celsius, 1.8 degrees Fahrenheit above a baseline, which conventionally is taken as the period from 1951 to 1980. And what you see is that even though the global average was 0.98 degrees Celsius increase over that baseline, across the Arctic, it was 2 to 4 degrees Celsius compared to the 1 on global average. And in the mid-continents, it was very often 2 degrees or more than as compared to that global average. So very non-uniform. And that's important for a number of reasons. One of the reasons is when the temperature changes are uneven, that produces changes in the circulation of the atmosphere and the oceans. And the changes, as noted before, are not just about temperature. Climate means weather patterns, meaning the averages, the extremes, the timing, and the spatial distribution of, hot and cold, but also cloudy and clear, humid and dry, drizzles, downpours, and hail, snowfall, snowpack, and snowmelt, breezes, blizzards, tornadoes, typhoons. Climate change entails disruption of the patterns. And global average temperature is just an index of the state of the very complicated underlying global climate system as expressed in those patterns. Small changes in that index, the global average surface temperature, reflect big changes in the system. It's very much like your body temperature. If your body temperature goes up 2 degrees Celsius, 3.6 degrees Fahrenheit, it's not the temperature per se that worries you, it's that it is telling you something is seriously amiss in that very complicated underlying system that is your body. Changes in climate matter because climate governs, and therefore altering climate affects the availability of water, the productivity of farms and forests and fisheries, the prevalence of oppressive heat and humidity, the formation and dispersion of air pollutants, the geography of disease, what pathogens and vectors exist in what numbers and with what vigor in what places, the damages to be expected from storms, floods, droughts, and wildfires, the property losses that have to be expected from sea level rise, expenditures on engineered environments, how much do we have to pay for dams, dikes, lifting up beach houses on pilings, and many other measures that we engineer. And of course, the distribution and abundance of species. The species we need, the species we love, the species we hate. Some manifestations of ongoing change. The extent and thickness of Arctic sea ice are shrinking. Top picture, September of 1984. Bottom picture, September of 2016. Drastic reductions of sea ice coverage at the September minimum. And in addition, the ice is getting thinner, which means the potential for future reductions is getting bigger all the time. Sea ice is floating ice, so its shrinkage does not affect sea level, but the change from ice to open water impacts regional temperatures, winds, storm damage, valued species, and as we will see, even affects the weather in mid-latitudes. The Greenland ice sheet is rapidly losing ice. Ice mass on Greenland is enough that if it all ended up in the ocean, sea level would go up by 23 feet. In fact, it takes a long time for that ice to disappear. We don't know exactly how long, but the pace of Greenland ice loss is a major contributor to the rate of sea level rise that is already being observed. Mountain glaciers are shrinking worldwide. This shows a historic picture from 1917 of the Athabasca Glacier in Alberta, and then a 2011 picture on the right of the same glacier from the same place. Drastic shrinkage, and again, that ice, which is now gone, has gone into the ocean and has contributed to sea level rise. That's happening in glaciers all around the world. We now know that Antarctica is also losing ice. A decade ago, we weren't so sure about Antarctica, but the measurements now have gotten much better, including satellites that can measure gravity differences associated with the thickness of the ice. And this NASA estimate from 2018 estimated that Antarctica is losing 127 billion tons a year of ice. But a very recent study in the Proceedings of the National Academy of Sciences found that the rate since 2009 was twice that, 250 billion tons a year. So it appears that the loss of ice from Antarctica is accelerating. The rate of sea level increase is then, not surprisingly, accelerating. This shows sea level rise from 1900 out to the present. And you see that from 1930 to 1992, the average rate of sea level increase was more than twice what it had been from 1900 to 1930. From 1993 to 2017, it doubled yet again. In fact, more than doubled. And if you actually run a curve through the very last period, from 2010 onward, it is almost doubled yet again. Sea level rise is accelerating. Climate change is already causing growing harm. This is very important. For years, scientists were arguing about when the goal of the Framework Convention on Climate Change that was agreed in Rio in 1992, the goal being to avoid dangerous human interference in the climate system, when might we start to experience dangerous? And the fact is, we have now been experiencing dangerous for some years. That goal is now moot. We can no longer prevent dangerous human interference because it's already happening. Around the world, we're seeing in various combinations increases in floods, in drought, in wildfires, in the power of the strongest storms, in heat waves and heat stress, in other harms to human health, impacts of crop and forest pests, coastal erosion and inundation, increasing permafrost thawing and subsidence, impacts of ocean acidification, warming, altered currents, and loss of sea ice on the distribution and abundance of valued species. All of that is happening. All of these effects are plausibly linked to climate change by theory, by models, and by observed fingerprints. The fingerprints mean the patterns in space and time with which these phenomena are emerging. And most of them are growing faster than was predicted just a few years ago. Let's look at some of these in detail. Warming causes bigger and more frequent torrential downpours. This is a graph of extreme one-day precipitation events in the contiguous 48 states from 1910 to 2015. And the physics here is rather simple. A warmer atmosphere can hold more water. And if it can hold more water, more can come down at one time, and it does. And in addition, moisture-bearing storm systems are moving more slowly in our warming world, so they stay over one place for longer and dump even more rainfall. Those downpours bring floods, 100-year floods, so-called, because historically their frequency was about once in 100 years, are now occurring once a decade or more in many places. Houston experienced 3 500-year floods, so-called, in 3 years. The picture here is from flooding in East Baton Rouge, Louisiana, August 2016, 20 inches of rain in 3 days. Houston got 50 inches of rain in 5 days in one of those 500-year storms. And of course, just this month, flooding in the Midwest in the United States has set new records for the region. Drought is exacerbated by climate change. You may wonder how that can be. How can we have more torrential downpours and more floods and yet also more drought? And here's how. First of all, higher temperatures lead to bigger losses to evaporation, drying out the soil. More of the rain falling in extreme events means more is lost to flood runoff, which means less moisture soaking into the soil, more soil drying. Mountains get more rain and less snow. That yields more runoff in winter, which leaves less for summer. Earlier spring snowmelt also leaves less runoff for summer and fall, and altered atmospheric circulation patterns are also playing a role. This is the U.S. Drought Monitor for September of last year, and you can see the intensity of drought. Yellow is abnormally dry. The very dark brown is exceptional drought. Large part of the country suffering from dry to drought conditions. Not just happening in the United States. This shows the 2 calendar years, 2015 and 2016, in the Amazon, how much of the Amazon was experiencing for those 2 years extremely dry positions, the magenta at the bottom. Absolutely extraordinary. There's a real danger, as we will see, that the Amazon over time will simply dry out. Recent wildfire history in the United States. There's a lot of year-to-year variability, but the trend The red line is absolutely unmistakably upward. One is now seeing something like 4 times the annual area burned by wildfires in the United States as prevailed in the early 1980s, a 4-fold increase in annual area burned by wildfires. And that comes from heat, drought, more dead trees as kindling that have been killed by pests that do better in a warmer world, and more lightning in a warmer world. Just continuing, the U.S. fire season is now 3 months or more longer than it was 40 years ago. The average fire is much bigger and hotter than before. 9 of the 10 biggest U.S. wildfires in recorded history all took place since 2004, the other one in 1997. 5 of those were in Alaska, where even now the tundra is burning, and smoke from today's big fires harms health over enormous areas. This is a picture of a tundra fire in Alaska in June of 2015. And here is a picture of the propagation of the smoke from fires in the northwestern United States, with heavy smoke pollution reaching all the way to New England as a result. Hurricanes and typhoons, tropical cyclones, are getting stronger. The largest and most powerful cyclones in history in nearly every ocean basin have all occurred since 2012. Absolutely astonishing increase in the power of storms. How does it happen? Tropical cyclones get their energy from the warm surface layer of the ocean. That layer is getting both warmer and deeper under climate change, and that means more energy is available for evaporating water from the ocean surface. Besides warmer surface water making a stronger cyclone, the deeper warm layer means that waves are able to churn up less cold water from the deep. That is the phenomenon that ordinarily limits the power of tropical storms. Their big waves churn up cold water from the deep, and that reduces the energy source at the Earth's surface by cooling the surface water. Now that the deep layer, that the warm layer is deeper, that phenomenon is weakened and the storms get stronger. This is a diagram showing that in the region that spawned Cyclone Haiyan in the Philippines, one of the strongest cyclones ever recorded, the heat potential available in the ocean surface layer in that area had gone up 20% since 1990, and the depth of the deep layer, which is the red curve, had similarly gone up. All else equal, there are a lot of different factors that govern the origin and the tracks of tropical cyclones, of hurricanes and typhoons. But all else equal, a given cyclone will be more powerful in a warmer ocean than it would be otherwise, and the higher local sea level is the worse the storm surge from any given cyclone will be, and very often the storm surge is the biggest source of the damage and the casualties. Now here's another very important point. It's a little bit technical, but it's worth pondering. It's why a modest increase in average temperature has led to large increases in heat extremes. Basically, this is a bell curve. Any normally distributed variable can be approximated by a bell curve which depicts the frequency of events at different places on the horizontal axis. So you have the initial climate on the left, and you see the probability of very cold events is kind of small. The probability of very hot events is kind of small. You move this distribution a little bit to the right. You make the average temperature a little bit warmer, and look at what happens at the hot extremes. There is a huge increase in the frequency of extreme high temperatures, and that, in fact, is exactly what we are seeing. These are record high temperatures that were set just in 2017 and 2018. These, in every case, are the highest temperature ever recorded in the indicated countries or cities. Highest ever recorded just in 2017 and 2018. And it's worth pointing out that it is now already the case in many parts of the world that working outdoors in the hottest months courts heat stroke. It is becoming dangerous to engage in construction, in forestry, in fishing, in agriculture in the hottest months, because the combination of temperature and humidity has exceeded the point at which the body can no longer get rid of the heat, and people get sick and they die. Direct impacts on human health includes, in the white on the upper left, of course, heat-related illness and death and cardiovascular failure, but there are many other direct impacts of climate change on human health. Asthma, cardiovascular disease, changes in vector ecology that affect malaria, dengue, encephalitis, and so on down the list, increasing allergens, longer allergy seasons, higher concentrations, causing problems, water quality impacts, water and food supply impacts. There is now a whole new program at Harvard run by Gina McCarthy, the former head of the EPA, focused entirely on climate change direct impacts on human health. Impacts of crop and forest pests. Pine bark beetles basically get 4 generations per warm season when they used to get only 3. That longer breeding season has enabled them to devastate trees already weakened by heat and drought in California, Colorado, and Alaska. Millions and millions of acres of trees killed, and thus both lost to recreational and economic benefit, but also kindling for the expanding wildfires. Rising sea level, coastal inundation because sea level has risen. This is, to me, one of the more astonishing graphics in this presentation. For all of these places on the East Coast, what we're seeing is the average number of flood events, circumstances where at high tide sea level is flooding streets in these cities. The blue bar at the top, 50 to 69, 50s and 60s, then the red, the 70s and 80s, the green, the 90s and first decade of the 2000s, and then the blue, the first half of the 2010s. Astonishing increase in the rates of inundation. Rising sea level, of course, also contributes to coastal erosion. This is from the Cape Cod Times, noting that Cape Cod is losing 33 acres a year to inundation and coastal erosion. Ocean acidification, about a quarter of the CO2 added to the atmosphere quickly ends up in the oceans. The dissolved carbon dioxide, by a very elementary chemical reaction, forms carbonic acid. H2O plus CO2 makes H2CO3, a weak acid. That lowers the pH, increases the acidity of the ocean. You can see the plot here from 1955 to 2015, atmospheric CO2. The partial pressure of CO2 in seawater is the green, and the pH is the declining blue. And that impedes the growth of organisms that make their shells or their skeletons from calcium carbonate. And that is a very large number of the crucial organisms in the ocean. It includes many zooplankton, it includes shrimp, crabs, oysters, clams, and this is a really big deal, a sort of a side effect. It's not climate change per se, it's the absorption of part of the atmospheric CO2 excess in the ocean. Coral bleaching, driven by rising ocean temperatures. The coral bleaching that took place over a period of 4 years, extending into 2017, was the longest and most widespread incidence of coral bleaching ever recorded, and was responsible for killing off a very substantial fraction of the coral in the northern Great Barrier Reef and very substantial fractions of coral in many other parts of the world. Other impacts on valued species, just a couple of journal titles here from recent publications about climate change and its impact on fisheries. The cod fishery in the Gulf of Maine, West Coast salmon survival rates being impacted. These are big deals economically. So that's what we've been observing. Let me turn now to what we expect, the future of climate change and its impact. And here's another quote I like. If you don't change direction, you'll end up where you're heading. That's what we have to worry about. We know that temperatures will continue to rise. How much they rise will depend strongly on the future of society's emissions. On the left, you see history out to about the present, that's the black, and then a series of forecasts depending on high emissions, medium emissions, low emissions of what the annual emissions of carbon dioxide in billions of tons of carbon content will be out to 2100. The high curve corresponds to a forcing of 8.5 watts per square meter by 2100. The low curve, a forcing of 2.6 watts per square meter by 2100. And what you see on the right is what the temperatures are expected to be associated with those different trajectories. And you see there's an enormous difference. The trajectory, the green trajectory, the very steep one on the left that declines very rapidly from here and goes down to essentially zero by the year 2100, ends up stabilizing temperature not too far above 2 degrees Fahrenheit, above the level in 1900. The high scenario, the red curve, which is pretty much business as usual, that's where we're heading if we don't take significant ameliorative action. That could end up with a global average surface temperature increase of 8 or 10 degrees Fahrenheit by 2100, and we'll see more about what that would mean. But the key point here is the biggest uncertainty about the future of climate change is what we decide to do about it. Some people say, oh, the models are uncertain, the science is uncertain. Yes, there are uncertainties in the model, there are uncertainties in the science, but by far the biggest uncertainty is concerning what we decide to do. If we do not achieve big emissions reductions, here's what we can expect. We can expect large increases in heat waves, a big further expansion in the area burned by wildfires, bigger torrential downpours and more flooding, destruction of most of the world's coral reefs, wider disruption of marine food webs and fisheries, more Category 3 to 5 hurricanes and typhoons making landfall, further increases in the intensity and frequency of droughts, falling agricultural yields for corn, wheat, rice, soybeans, more sickness and deaths from heat stress and tropical diseases, sea level rise that could reach 1 meter, 3.3 feet by 2050, and could reach 2 meters, 6.6 feet by 2100. And as a result of all of this, much bigger flows of environmental refugees, and all that means for international stability and national security. Just to illustrate a couple of these points, hotter summers, this shows for the world the percent of summers that by around 2040 will be warmer than the current 95th percentile hot summer. And what you see is over most of the world, 90 to 100% of summers by 2035 or 2040 will be hotter than the hottest 5% of summers are today. Droughts expected to increase over much of the globe. This is a little complicated. You might have to go look at this when it's posted, but the top figure is a baseline 1961 to 1990. How many 4 to 6 month duration droughts occurred for every 30 years in these different places? And you see that most of it is in the purple and the blue and the turquoise, less than one 4 to 6 month drought per 30 years. And then you look at what is expected in the last part of this century under one of the higher emission scenarios. Not the highest, but a relatively high one where we don't do very much. And you see that over enormous parts of the area of the planet, the number of droughts per 30 years, severe droughts per 30 years, has gone up to the range of 4 to 4.5 to 5 or 6 times what it was in the baseline period. This is, again, a little complicated, but this is the Princeton hurricane model, widely regarded as probably the best model of the connection between global climate change and hurricane frequency and power. And what it shows is that by the end of this century, there will be more frequent landfalls for the United States, particularly major hurricane landfalls, 3 to 5, Category 3 to 5. And you see this extends all the way up through New England and into Maine and beyond. The difference in landfalling major hurricanes per decade for the last part of this century, and the 1986 to 2005 period is what the scale represents, and you see multiples of up to a factor of 2, twice as many Category 3 and 5 hurricanes making landfall. So here is an animated picture of eastern Massachusetts showing different levels of sea level rise. 1 to 2 meters expected by 2100, 3 to 12 in the next few hundred years, up to 70 meters eventually. And you see that basically the Cape goes away in the long term in this future, and big parts of it go away even in this century. Woods Hole will become a series of islands with just a meter of sea level rise. So other impacts likely to affect Cape Cod: saltwater intrusion into freshwater wetlands and aquifers, compounded by increasing pumping of groundwater to serve a growing population, more frequent, more intense, longer red tides and shellfishing closures, additional threats to lobsters and mollusks from bacterial and other diseases that flourish in warm water, damage to native marine species by invasives from warmer regions, reduced abundance of northeast bird species, and increased winter weather extremes. And I'll just show you here how it can be, again, that in a world that is warming overall, we can see more severe winter weather in the eastern United States. This is a so-called polar vortex phenomenon, where the fact that the poles are warming more rapidly than the mid-latitudes means that the temperature difference between the pole and the mid-latitude is shrinking. That shrinking temperature difference makes a weaker jet stream a wavier boundary between the cold polar air and the warmer mid-latitude air, and that produces cold air excursions into the south and warm air excursions into the north. So you get these phenomena which we've seen in recent winters, where you get record cold in the eastern United States while record warmth is occurring in Alaska at the same time. That's the wavy boundary of the polar vortex. So what we can do, and I like this quote as well, this is from my former colleague in the White House, Jake Sullivan: "Between fatalism and complacency lies urgency." Society has, in the face of the climate change challenge, only 3 options: mitigation, the measures you take to reduce the pace and the magnitude of the changes in global climate that we cause; adaptation, measures that you take to reduce the adverse impacts on human well-being resulting from the changes in climate that you fail to stop, the changes that do occur; and the third option is suffering. Suffering, the adverse impacts and the societal disruption that are not avoided by either mitigation or adaptation. Mitigation possibilities include reducing the emissions of greenhouse gases and soot from the energy sector, reducing deforestation, increasing reforestation and afforestation, modifying agricultural practices to reduce emissions of greenhouse gases and build up the carbon stored in the soil. Some of these measures will be costly, but they will be less so than unmitigated climate change. Conceivably, we might ultimately resort to a couple of other things. One is scrubbing greenhouse gases from the atmosphere technologically. Trees are nature's way of removing CO2 from the atmosphere, but we can't grow enough trees to solve the whole problem, and we are already exploring ways to suck carbon dioxide out of the atmosphere technologically. It is very expensive, and people are working on how to make it cheaper, but it is questionable how much cheaper it can be made. Another conceivable option is geoengineering, to try to create cooling effects that offset some of the greenhouse heating. That is, according to studies to date, limited in efficacy and has a number of potentially troublesome side effects, but society might still be driven to experiment with it. Lots of adaptation possibilities listed here. The interesting thing about these adaptation possibilities is that many of them are what are often called win-win measures. They're things that would make sense even if the climate were not changing. Because we've always had wildfires, we've always had powerful storms, we've always had floods, and we've always been underprepared. It would pay to increase our preparedness, to increase our resilience against these kinds of events, even if climate change were not making them more frequent and more severe. And so they mostly look like bargains, but still, we are not doing enough of them. We are already doing some mitigation, we're already doing some adaptation, and as you've seen, we're already doing some suffering. What's at stake is the future mix. And if we want to minimize the amount of suffering in that mix, as we should, we can only achieve that by doing a lot of both mitigation and adaptation. They are not substitutes, they are complements. Mitigation alone won't work because climate change is already occurring and cannot be stopped overnight, no matter what we do. Adaptation alone won't work because adaptation gets costlier, more difficult, less effective as the amount of climate change to which you're trying to adapt gets bigger. So what we need is enough mitigation to avoid unmanageable climate change and enough adaptation to manage the unavoidable climate change, the climate change that we can no longer stop. How much mitigation do we need? The community of nations agreed in 2009 on a goal of holding the increase in global average surface temperature to 2 degrees Celsius, 3.6 degrees Fahrenheit above the pre-industrial level. That target was picked not because it would keep the world safe, but because it was the lowest figure that experts thought might be achievable. But the adverse impacts already being experienced at today's 1 degree C increase over the pre-industrial level had led the hardest hit countries to argue in the Paris conference in 2015 that 2 degrees C would be unacceptably devastating and that the world should aim for 1.5. And that led to a call from the Conference of the Parties to the Intergovernmental Panel on Climate Change to study the difference between 2.0 degrees Celsius and 1.5, and to look at what would be needed if you tried to get the temperature increase stopped at 1.5 instead of 2. And what they found, they underscored the point that had been made in the 2015 conference by a number of the hardest hit countries, that 2 would be a disaster. At 2 degrees C, they found we would lose 90% of the world's coral reefs, for example, among many other impacts. At 1.5 degrees, we would lose about 44% of the coral reefs. So even 1.5 is not safe. 1 isn't safe. We're already experiencing consequences. But staying below 1.5 would be very, very demanding. These are emissions pathways that would produce a good chance of staying below 1.5 degrees. And you see they require essentially immediate, very steep reductions in global emissions of carbon dioxide and somewhat slower emissions of the other major greenhouse gases. So this report, the 2018 report of the IPCC, was really a wake-up call. They didn't even look at the consequences of global average temperature increases of 3 or 4 degrees. They just looked at 1.5 and 2. They said 1.5 is much worse than 1, where we are now, and 2 is much worse than 1.5. But the fact is that temperatures in the range of 3 or 4 are the most likely result of continuation of the current slow progress in technological and policy innovation. The recent conclusions that the IPCC reached about 2, as well as earlier IPCC studies and others that looked at temperature increases of 3 or 4, make completely clear that increases of 3 or 4 would be a climate catastrophe, a world changed beyond all human experience, unlivable over much of the land surface in the hottest months, plagued by greatly amplified floods, droughts, and wildfires, racked by storms more powerful than the worst of today's. We might need to define a new category 6 for hurricane power. And former coastal cities flooded by sea level rise. What can the federal government do? Well, in the Obama administration, we boosted climate research and monitoring. We invested in clean energy R&D and incentives for the private sector to do the same. We put forward aggressive energy efficiency standards, promoted climate change adaptation with many different executive orders, including requiring every single federal department, agency, and office to build in climate change adaptation to every budget, every program, every project. We launched a climate action plan with a comprehensive set of measures, everything you could think of to do with executive authority, because we couldn't get the Congress to help. With an extraordinary effort, we reached agreement with China that led basically to the other developing countries jumping on board and achieving the Paris Accord with 195 countries. What has the Trump administration done? They put climate contrarians in charge at the Office of Management and Budget, the EPA, the Department of Interior, the Department of Energy. They left many key science positions unfilled. They proposed deep budget cuts in climate science and clean energy R&D, canceled Obama's climate action plan and executive orders on adaptation, and announced the U.S. withdrawal from the Paris Accord. The damage by Trump is significant, but it is limited. First of all, the United States cannot formally withdraw from the Paris Accord until 2020, but what Trump has done is halt most of the federal government's efforts to comply with it. The most damaging potential consequences: loss of U.S. credibility and moral authority worldwide, elimination of federal standards affecting U.S. emissions, cuts to our climate change assistance to other countries, and cuts to government-funded climate research and energy R&D. Nonetheless, many states, cities, companies, universities, civil society organizations, and individuals are taking positive steps still to meet the Paris commitments. There's something called the America's Pledge, and the motto is we're still in. We're still in the commitment to reduce U.S. emissions by 26 to 28% by 2025. There are something like 22 states, hundreds of cities, 1,000 businesses, hundreds of universities, and countless citizens who are engaged in taking constructive action. We have to do more. I believe that just keeping the temperature increase below 2 degrees Celsius is going to require a global carbon tax, starting soon at around $30 per ton of carbon dioxide equivalent, increasing to at least $100 a ton by 2030. Preferably, it would be collected by national governments, and it would be rebated on a per capita basis, which makes it progressive. The poor people would get more money back than they spent in the extra carbon fees. Rich people would get less money back than they spent in additional carbon fees. That would incentivize using the best available low and no emission technologies now and investing in research, development, and demonstration to get better ones. We will need a massive program of technological innovation on clean energy and energy efficiency. That program should be advanced through partnerships among government, industry, and universities. That was being promoted by the Obama administration. It would include all of the items listed here. Not all of them will work, but we need to be pushing on everything to see how many of the ingredients of drastic reductions in greenhouse gas emissions we can get. And we need a similarly massive set of public-private university partnerships focused on developing and implementing adaptation measures to limit the harm from the changes in climate that we can no longer prevent. I think the political will to get all this done might actually materialize faster than most people think, because of the combination of rapidly increasing damages from climate change, which increase the incentives to act, and declining costs of remedial action as a result of innovation. So the incentives are going up, the costs are going down. I think we're going to reach a tipping point where everybody finally understands that action is much cheaper than inaction. What should everybody do? Increase your understanding of the challenge and the remedies, share those insights, reduce the carbon footprint of your own home and your transportation habits, encourage the mitigation and adaptation activities undertaken by your state and local governments, support businesses and civil society organizations that are taking constructive action, vote, and even better, work for political candidates who understand the challenge and pledge to act. Trend is not destiny. Thank you very much.
Will you take questions?
I will. I say to my classes, questions, comments, or cries of outrage.
Would you say something about what's happening with the flow of young people coming into the sciences, whether the the current views of national leaders notwithstanding, whether more are coming in, less coming in, and in that regard, what role foreign-born potential scientists play for us in this process?
Those are really interesting questions. First of all, I don't have any up-to-date data on the overall flow. I have a biased sample. I interact most heavily with Harvard, MIT, Tufts, Berkeley, Chicago, Michigan, and in those places, the flow is not declining. But I can't say for the nation as a whole what's happening to the flow. There are some indications out there that many smart young people have decided to go into finance where they can make a lot more money than in science. Engineers are still among the most highly paid college graduates, particularly engineers in the information technology fields, but we may be losing out in some measure to financial incentives on the choices that students make about fields. I see no reduction in interest and enthusiasm for addressing the climate change challenge. Again, I have a biased sample, but I'm seeing a tremendous amount of energy and enthusiasm and competence and focus out of young people on the energy climate challenge, as well as on a number of the other challenges that we face in our society. Healthcare, for example, sustainable agriculture, water supply. I think the biggest source of hope, in fact, is the generation coming along that we can expect will do better than our generation has done.
Over there.
Dr. Holdren, could you clarify the difference between remedial action and mitigation? And I think your second last slide, you said the cost of remedial action was coming down.
It is, but remedial action means both mitigation and adaptation. And as I use remedial action to refer to everything we do to try to reduce the harm to human well-being that arises from climate change. And the costs that are coming down most rapidly, and your question may be suggesting this, are the costs of mitigation. The costs of adaptation vary widely. Some of them are win-win solutions that are essentially free because we should be doing them anyway. Some of them are going to be considerably more expensive. But when I look at the likely damages from climate change if we do not make these investments in both mitigation and adaptation, my own conclusion, and I think that of most economists who've looked at this question, is that action is going to be much cheaper than inaction.
Question here.
Thank you so much for your talk. So we're going to lose our current agricultural land from climate change. And so I'm wondering, you know, as certain parts get warmer, is that going to open up agricultural land, or does it take, you know, years and years to actually develop new agricultural land?
It's actually a complicated question. We're not going to lose all of the current agricultural land, but it's going to be more difficult to sustain its productivity, never mind increase it. As climate patterns change, there will be some areas that become suitable for some kinds of agriculture that were not suitable before. Already we are seeing, for example, wine production in parts of the world that never had it before. England is producing wine grapes now and producing decent wine. Nobody ever thought that would happen. And so, but here's a crucial point about this, really crucial point. The analyses that have mostly been done that show that in some places you'll be able to grow stuff you couldn't grow before are based on changes in the averages. And much more important than the change in the average temperature or the average precipitation is the changes in the extremes. Torrential downpours, hailstorms, wildfires, and floods are bad for crops, no matter what the average changes have been.
Over there.
Dr. Holdren, I want to thank you for presenting tonight and also for your past work with the Obama administration. The question I have relates to carbon pricing. So I've done some research on this. I was actually trained in atmospheric science originally in my undergraduate studies, and I did some research into carbon pricing. When I've done the math and I've thought about the carbon pricing issue, one of my concerns is that if we don't take sufficient action soon, what we might witness is an initial low pricing of carbon per ton. And then as the damages continue to accrue and we realize how much we have to drive up the price of carbon to spur innovation and start lessening the demand, it would be such a leap in cost that it would be the equivalent of producing a massive sticker shock or shock to the economy. Like, I've seen some research suggesting that ultimately the carbon pricing should be something like $1,000 per ton. And obviously research is going to bear out different scenarios, but can you speak a little bit to the issue of successfully pricing carbon at a suitable initial value?
Yeah, there has been a lot of serious work about this, in fact, fortunately, and the short answer is there are certainly ways to do it wrong as well as ways to do it right. And we need to obviously choose the right way. The proposal that I put on the screen, starting around $30 a ton, is one we actually looked at quite carefully in the Obama administration and found, for example, that if we imposed a tax of $30 a ton, which unfortunately would require the Congress to go along, and so we never even proposed it because we knew it would be laughed out of the Capitol by the Republicans in the Congress. But we found if you had put a price of $30 a ton, what the economic modeling showed, it would not do any significant damage to the economy, but our emissions in 2025, instead of being 26 to 28% below, which was the goal we announced as being achievable without a carbon tax, would have been 32 to 34% below, just with $30 a ton over the period from now till 2025. There is no question that $30 a ton will not wreck the economy. $30 a ton would actually only increase the price of gasoline by 30 cents a gallon. And as we all know, the price of gasoline goes up and down by more than that in a week for reasons nobody can explain with both hands above the table. Even if you got to $100 a ton, if you got there gradually, it would not, in all likelihood, damage the economy significantly. And there have been many economic studies to show that. $1,000 a ton would be a different matter. But people who argue that ultimately you'll need $1,000 a ton are not counting on any innovation at all. And in fact, innovation has enormous potential for lowering the cost to within reach of reasonable carbon taxes.
Question here.
Yeah, so, we're a community of people, and most of us will then leave your talk and get into our cars, some of them SUVs and trucks, and drive away and, say, oh, yeah, something really has to be done. In terms of the community, in a community level action, are there things going on? Are there places we can go and talk to get people to be a little more aware of the things like working on your houses, working on your driving habits?
There is still in existence on the government web something called the Climate Resilience Toolkit. And the Climate Resilience Toolkit is a very user-friendly, substantial database and set of case studies that looks at the most significant climate change impacts expected in different parts of the country or ongoing in different parts of the country, and provides instructions as to how to take action to ameliorate those particular harms. That's on the adaptation side. On the mitigation side, clearly the cheapest, fastest, safest, surest way to reduce emissions is to increase the efficiency with which energy is used to deliver the goods and services that people want. Part of that is technological. Part of it is behavioral. For example, for many of us, our biggest carbon footprint is the number of meetings we fly to every year. In fact, recent studies at Harvard suggest that the faculty has a carbon footprint 2 to 3 times higher from flying than everything else they do combined. That means if you can start substituting video conferences for some of your trips, you can save a lot of energy and reduce a lot of emissions. There are many other measures you can take. You know, the Woods Hole Research Center, which built its new building now about a decade ago, has a building that with the wind turbine and the photovoltaics on the roof, most of the time is generating more energy than it's using and selling the excess to the grid. It's a comfortable building, a wonderful place to work. We can ultimately convert all of our buildings to basically net energy and emission zero structures and save money on energy while doing it. There is an enormous amount of information out there. We spent a lot of effort in the Obama administration trying to package it in ways that people could get at it and understand it and use it. Some of that effort has flagged in the current administration, but some is still going on. And again, we have cities and states and non-governmental organizations doing a lot of this now. So if you actually look around, you'll find there's a lot of information out there about what people can do to reduce their own emissions. In the end, all of those things won't be enough if we don't get the government to take action. And that's why at the bottom of my list, I say vote for candidates and work for candidates who are going to take this seriously as a matter of national priority, because we are going to need the federal government in the game if we're going to get enough of this done. And by the way, we need the federal government in the game if we expect other governments around the world also to stay in the game. I guess we got one more.
Good evening, Dr. Holdren. In terms of causal factors and trends, there's rarely a discussion of the trend of population increase, human population increase. And is there any correlation, or is it that relevant if it just continues as it goes?
No,
but it's rarely brought up in any, like there's not a curve in any of your slides, for example, that shows increases in the population connections.
I didn't show it separately, but the very first slide showed that population and rising affluence together produced this more than 20-fold increase in energy use, which of course produced, because the energy came mostly from fossil fuels, this huge increase in greenhouse gas emissions. The population issue became kind of a political hot potato in the 80s and 90s. A lot of countries resented the discussion about population growth and thought it was either imperialistic or racist. And a lot of the emphasis in the global issue with respect to population turned to what has proven to be the most effective leverage against it, which is improving education and opportunities in healthcare for women. And around the world, population growth rates have shrunk as women gained better access to healthcare and contraception, better access to education, better access to other opportunities. We did a study, I was involved in a study that was completed in 2007 for the UN Secretary General that did look explicitly at the population growth component and showed very definitively that if we have 8 billion people in 2100 rather than 12 billion people, and that's sort of the range of reasonable possibilities at this point, it is far easier to get your arms around the climate change challenge and many others if we have 8 billion rather than 12. And if we could get back down to 7, that would be even better. So there really is no question about what the numbers show, but there's a lot of question about how to advance the issue. And as I say, the most widely accepted way to advance the issue is to work on the women's angle.
Before we thank him, I want to remind everyone, you had this brochure that you got at the door, or as you came in, and the form at the bottom is the one that, well, if you have a pen, you can do it now. Fill it out, make a donation to the Falmouth Forum Endowment Fund, and maybe next year, John will come back.
Thank you.
Thank you. Maybe next year we can talk about fishing. Yeah. Yeah.
Thanks, sir.